இந்த ஒரு ஒயிட் இருந்தது. ஒயிட் போடு. லைட் yellow. White. Okay. This better?
Check. Yes. I can read. This will be audible, no? If I read from here. It is.
Say something. கேக்குறதா?
Hello.
இல்ல இவங்க பேசுறது கேக்குறதா? Just read something. Read something.
Sir, I have to. Yeah, Abhinav Sapra.
கேக்குறது. Okay. Fine.
Yeah.
So I leave this here. The opening batsman.
So this is after Madhavan declares let the candidates be presented. Okay.
Right. Maybe you should say let Siddhi be presented, then let the candidates be presented. Get the cue that you have to come on stage.
Yeah. No. Today I will remember the photograph.
Hello, mic checking. 1, 2, 3. Hello. Okay.
இதோ வரேன். ஜி இது ஓகேவா? இதுக்கு மேலே வரால.
We have a head mic also.
That's good.
Yeah.
Hello?
Yeah. What are that?
Hello? Hello? Mic testing?
Yes.
Okay.
Check.
Okay.
Yes. Okay. I'll be here. The pencil is also here. Okay. So I'll switch it off. Okay. Pen paired again. So I'll just keep it on top of this. I'll keep it attached to the. Yeah, I think இப்போ இது கழட்டிடலாம் இல்லையா வேணுங்கும் போது போட்டு விடலாம் இல்லையா இப்படி எடுத்து விடலாம் ஏன்னா அந்த பவரும் அது இழுத்து முடியாது ஸோ இந்த சார்ஜில் இப்படி இருக்கணும் திஸ் இஸ் லிட்டில் பெட்டர்
Good afternoon and welcome. It gives me great pleasure to welcome all of you to the 22nd Convocation of the Chennai Mathematical Institute. We are very happy to have Professor Jaikumar Radhakrishnan as a chief guest at our convocation. Professor Radhakrishnan is currently a senior professor at the International Center for Theoretical Sciences, ICTS, of the Tata Institute of Fundamental Research, TIFR, in Bangalore. Prior to joining ICTS, he was a faculty member at the School of Technology and Computer Science, TIFR, in Mumbai for over 30 years. Professor Radhakrishnan received his master's and PhD degrees in computer science from Rutgers in 1991, prior to which he had completed his BTech in computer science and engineering from IIT Kharagpur in 1986. He has been awarded the Shanti Swarup Bhatnagar Prize. He is a fellow of both the Indian Academy of Sciences and the Indian National Science Academy. So after his PhD, Professor Radhakrishnan came back to India and he joined TIFR in 1991. And his main areas of research have been complexity theory, randomness and computing, quantum information and computing, combinatorics, and information theory. So he played a very key role in rebuilding the theoretical computer science group at TIFR, but he also has been an inspiration to the younger generation of computer science researchers in India. So he has played a major role in building up the theoretical computer science community across the country. He is very well known, of course, for his technical expertise, but also for his clarity of thought and his exemplary expository skills. He is an old friend of CMI, and for instance, last year he helped us coordinate a semester-long program on quantum computing here at CMI. So welcome to CMI, Professor Radhakrishnan. So a few words about CMI, which will be familiar to those who have come before, but maybe for some who are new in the audience. So CMI's strength is in combining world-class research with high-quality teaching. So the students who come to CMI are among the brightest minds in the country. A large fraction of our alumni pursue higher studies, and several of them are distinguished academics in their own right. In recent years, CMI graduates have also taken up challenging industry positions in diverse areas. So leading companies in sectors ranging from investment and finance to manufacturing and technology visit CMI for campus hiring. On the academic front, CMI has strong research ties with leading institutions across the country and around the world. In addition to bilateral projects with researchers in Europe and the US, CMI hosts an international lab in computer science and mathematics under CNRS, the French National Center for Scientific Research. CMI also regularly hosts visitors who deliver research seminars, teach short courses, and interact with the faculty and students at CMI. In an effort to expand its research footprint, in 2020, CMI announced a new center of excellence named after Dr. F.C. Kohli, the founding father of India's IT industry. The center has already started its activities. It's hosting programs such as seminars, instruction schools, and workshops. One of the early activities of the center has been a partnership with the Banff International Research Station, BIRS, to hold one-week research workshops around the world, throughout the year. Since 2024, CMI has hosted workshops on a variety of topics, from number theory and quantum computing to network models and the interplay between statistics and machine learning. 8 more workshops are scheduled between August this year and January of 2026. In February of 2026, we will also be hosting a winter school on topological data analysis. And this is part of a new effort, a coordinated series of summer and winter schools across the affiliate institutions which work with BERS. A few years ago, CMI acquired additional land within Sipcot IT Park, which is quite nearby to this campus, about 1 kilometer away. And this campus will host a new facility to host research workshops and conferences. Construction began about a year ago and is progressing well, and we hope that the facility will become operational during the coming year. Over the last decade, CMI has also been making active efforts to engage with both industry and the government. In 2015, CMI set up a society called Algo Labs, which undertakes training programs and consulting projects with industry in all areas related to the mathematical sciences, including analytics, optimization, and machine learning. There have also been efforts to engage with the state government through the Tamil Nadu e-governance agency, the TNEGA. One of the visions that the founder of CMI, Professor Seshadri, had was that it should also grow into a multifaceted university. Along with this, the CMI Arts Initiative was launched in 2012 to provide opportunities for students and faculty at CMI to interact and learn from experts in the arts and humanities. So CMI regularly hosts programs under this initiative in topics such as literature, art, music, history, and cultural heritage. Despite CMI's modest size, it has had a fairly large impact on the research environment in the country. About 60 alumni are currently faculty members at the top academic institutions in India. In recent years, as I mentioned before, CMI alumni have also been joining the industry in large numbers. CMI is also playing an active role in popularizing mathematics among younger students. CMI hosts the training camps for the International Mathematics Olympiad and the International Olympiad in Informatics, as well as the European Girls Mathematics Olympiad. The new campus that is under construction will have a mathematics museum of sorts, which will have exhibits designed to expose more students to the world of mathematics. And recently, CMI has also been started to work with the state government's departments of school education and higher education to try and improve the quality of math education across the state. So CMI is unusual in Indian academia in that it receives substantial funding from both the government and industry, not to mention several enlightened individuals. We would like to acknowledge the generosity of the National Board for Higher Mathematics, the Shriram Group companies, Cognizant Foundation, Trumpf Metamation, Mr. R. Tyagarajan, Mr. Lakshmi Narayan, Mr. Prem Kumar Tatineni and Mrs. Sujata Prem Kumar, Ms. Nirmala Govindan and Mr. S. Mahalingam, who, among others, have played a big role in bringing us to the place that we are today. I once again welcome all of you and declare the convocation open. Let the candidates be presented.
Sir, I have great pleasure in presenting to you 14 candidates who have successfully completed the National Undergraduate Program in Mathematics and Computer Science at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Computer Science. Aditya Kannan, Ananya Rajas Ranade, Anush Sanjay Rao, Abhishek Hazra, Chandralekha P, Dyuti Mukherjee, John Tom, Krishanu Bandopadhyay, Nirjar Nath. Sahil Lakhmani. Shyam Vishwas Patankar. Suchir Kaustav. Gautam S. Vishwanathan. Gaurab Ghosh.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Bachelor of Science Honours in Mathematics and Computer Science, and in witness thereof, you have been presented the diplomas.
Please come ahead for the Sir, I have great pleasure in presenting to you 19 candidates who have successfully completed the National Undergraduate Program in Mathematics and Computer Science at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Computer Science in absentia. Aditi Mishra, Ashish Ranjan, Kaushan Saha, Malay Devashish, Mayur N. Sastri, Priyangshu Ghosh, Ritvik Bhattacharya, Ryan Hota, Satyen Jha, Sayandeep Sheh, Soham Ghosh, Subham Mal, Sumit Rajput, Vardhan Kumar Ray, Amit Parikh, Ishan Verma, Sabavarup Dhanush Reddy, Shakti Chauhan, Shashwat Asthana.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of the Bachelor of Science Honours in Mathematics and Computer Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 3 candidates who have successfully completed the National Undergraduate Program in Mathematics and Physics at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Physics. The list of students is Aditya Seth, Harini Ram Mohan, Vedant Nima,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Bachelor of Science Honours in Mathematics and Physics, and in witness thereof, you have been presented the diploma.
Sir, I have great pleasure in presenting to you 7 candidates who have successfully completed the National Undergraduate Program at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Physics in absentia. The students are Anhat Chaturvedi, Onkon Mukherjee, Neelaksh Vyas, R. Balaji Yadav, Rajashi Ghosh, Adarsh V, and Ripunjay Dwivedi.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Bachelor of Science Honours in Mathematics and Physics, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 3 candidates who have successfully completed the National Graduate Program in Mathematics at Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Master of Science in Mathematics. Ojas Kumar, Soham Pal, Shubham Katiyar,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Mathematics, and in witness thereof, you have been presented the diplomas.
Sir, I have great pleasure in presenting to you two candidates who have successfully completed the National Graduate Program in Mathematics at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Master of Science in Mathematics in absentia. Yeduraj Rao, Balaji Subramaniam.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of the Master of Science in Mathematics, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 7 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Computer Science in the year 2025 and are eligible to receive the degree of Master of Science in Computer Science. Abhinav Sapra. Akhauri Shauryam. Aritra Mazumdar. Jessica Vipin. Shobhit Singh. Subhaman Supantha. Ritika Sarkar.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Computer Science, and in witness thereof, you have been presented the diplomas.
Sir, I have great pleasure in presenting to you 7 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Computer Science in the year 2025 and are eligible to receive the degree of Master of Science in Computer Science in absentia. Ankan Kar, Aryan Joshi, Dipro Sarkar, Rishikesh Saikia, Sai Shashank Y, Sayan Bose, Sunit Nitin Patil.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Master of Science in Computer Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 34 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Data Science in the year 2025 and are eligible to receive the degree of Master of Science in Data Science. Alekhya Mukhopadhyay. Alina Maria Thomas. Alok Dhar Dubey. Ananya Kaushal. Ananya Sinha. Aniket Tiwari. Ankita. Aparna C. Arka Roy. Aryansh Raj Saxena. Atul Anant. Vivek Paul. Divyanshi Kumari. Suryadeva Iada. Isha Bhattacharya. Gaurango Kumar Baishya. Hiba AP. Himanshu. Keshav Kumar. Kiranmoy Roy. Malde Dharmi. Mayank Nagar. Nandini Jaiswal. Narendra C. Om Ambe. Rohit Roy. Samaroha Chatterjee. Satik Biswas. Satyaki Malik. Sayantani Saha. Siddhesh Maheshwari. Soumya Joy Kundu. Srija Chaudhary. Suneha Sen.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Data Science, and in witness thereof, you have been presented the diplomas.
Sir, I have great pleasure in presenting to you 21 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Data Science in the year 2025 and are eligible to receive the degree of Master of Science in Data Science in absentia. Aishwarya S., Aman, Ashish Bisht, Ayush Yadav, Bhuvanesh Sahu, Chandranath Bhattacharya, Dipanshu Mittal, Dipanjoy Saha, Himanshu, Jerin Biju, Kalyani Vijay Gohokar, Nuh Ali, Pritam Padhan, Salokya Deb, Shauvik Ghosh, Soumya Das Gupta, Utpal Raj Kemprai, Vikas Chaudhary, Vishal Maurya, Devmalya Biswas, and Narendran Ramakrishnan.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Master of Science in Data Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 3 candidates who have successfully completed the degree of Doctor of Philosophy in Mathematics at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Doctor of Philosophy in Mathematics. Prithijit Biswas, Nirmal Kotal, Krishna Menon.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Doctor of Philosophy in Mathematics, and in witness thereof, you have been presented the diplomas. We'll do a group and then we'll continue.
Me? Let's finish. Sir, I have the great pleasure in presenting to you one candidate who has successfully completed the degree of Doctor of Philosophy in Computer Science at the Chennai Mathematical Institute in the year 2025 and is eligible to receive the degree of Doctor of Philosophy in Computer Science. Srinidhi N.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Doctor of Philosophy in Computer Science, and in witness thereof, you have been presented the diploma.
Sir, I have great pleasure in presenting to you two candidates who have successfully completed the degree of Doctor of Philosophy in Computer Science at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Doctor of Philosophy in Computer Science in absentia. Archit Chauhan, Somnath Sudam Dake.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Doctor of Philosophy in Computer Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you two candidates who have successfully completed the degree of Doctor of Philosophy in Physics at the Chennai Mathematical Institute in the year 2025 and are eligible to receive the degree of Doctor of Philosophy in Physics in absentia. Pankaj Saini, Partha Pratim Mahapatra.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Doctor of Philosophy in Physics, and in witness thereof, they have been presented the diplomas in absentia. So we have completed the handing out of the formal degree certificates. CMI also has some special awards for those who have performed very well in their undergraduate and master's programs. So I will just briefly describe the awards and then we will get to the presentations. So we have gold medals for each of the programs for Bachelor of Science in Mathematics and Computer Science, BSc Honors in Mathematics and Physics, MSc Mathematics, MSc Computer Science, and MSc Data Science. So there are 5 gold medals. So these gold medals initially were instituted by Professor K.R. Nagarajan, who was one of the early people who helped shape the program. And then we had some endowment from Bajaj Alliance and Professor Gauri Vishwanathan, and CMI has also chipped in over the years. So this is a kind of jointly funded set of gold medals. In addition, we have some special awards which have been instituted by individuals who are well-wishers of the institute. So Sri Arun Dugal, through the Sri Ram Ownership Trust, has instituted 2 awards, the Arun Dugal Award and the Dr. Rita Dugal Award. So the Arun Dugal Awards go to the best female student in the bachelor program in mathematics, and the Rita Dugal Award goes to the best female student in the master's program in computer science or mathematics. And finally, recently, Sri Jeevan Kapoor has instituted an award in the name of Mrs. Chandar Mohini Kapoor and Mr. Jeevan Kapoor. This merit award is given to the best performing female student in the master's in data science program.
The Arun Dugal Award for the best girl student with the highest GPA in BSc Honors in Mathematics and Computer Science goes to Ananya Rajas Ranade. The Sri Arun Dugal Award for the best girl student with the highest GPA in BSc Honors in Mathematics and Physics goes to Harini Ram Mohan. The Dr. Rita Dugal Award for the girl student with the highest GPA in MSc Mathematics or Computer Science goes to Ritika Sarkar. The Mrs. Chandar Mohini Kapoor and Mr. Jeevan Kapoor Merit Award for the girl student with the highest GPA in MSc Data Science goes to Ankita. Now for the CMI Gold Medal of Excellence. The CMI Gold Medal of Excellence in BSc Honors in Mathematics and Computer Science goes to Suchir Kaustav. The CMI Gold Medal of Excellence in BSc Honors in Mathematics and Physics goes to Aditya Seth. The CMI Gold Medal of Excellence in MSc Mathematics goes to Soham Pal. The CMI Gold Medal of Excellence in MSc Computer Science, Aritra Majumdar. The CMI Gold Medal of Excellence in MSc in Data Science goes to Siddesh Maheshwari.
So I now request Professor Jaikumar Radhakrishnan to deliver the convocation address.
Usually once the notability comes up, it won't be this. Switch it. Yes, I think yes.
Good afternoon, everybody. Yeah. So, yeah, I'm very grateful to the Chennai Mathematical Institute to invite me to give this year's convocation address. I mean, they're all my friends, of course, and I remember bicycling all the way from Tiruvanmiyur to G.N. Chetty Road when the Chennai Mathematical Institute, maybe it was called something else then, was located there to attend talks and maybe sometimes give talks. But this invitation actually demanded, I think, extraordinary courage and bravery from their point, from them. Because the last time I was on this stage, various disastrous things happened. Yeah, so that door there blew in, and we were all told not to leave this auditorium for a good 4 hours. So I hope not to bring the house down this time. And yeah, so I'm a theoretical computer scientist with interests in discrete mathematics and probability information theory. So I've planned a talk which I hope is accessible to many of you and gives you an idea about this topic called the probabilistic method. Yeah. Before that, especially, I would like to congratulate all those who received their degrees today. I know, my friends are demanding teachers, and you have made it through. You ought to be proud of yourself, and I also commend the support that you received from your parents and guardians through these years, and I wish you the very best for the future. So, yeah. So the plan for today is I'll tell you what the probabilistic method is, and it will be something of a technical talk, but I'll try to keep it at a level which I hope everybody can understand. And yeah, so please try to understand as much as you can. Okay, so I'll just tell you what the probabilistic method is, and then I'll tell you an example, I'll tell you another example, and another example. And then we can go for tea. Yeah? Okay. So, yeah, the probabilistic method today is attributed, or at least the version that I'm familiar with, is attributed to Paul Erdős, who's a famous Hungarian mathematician with contributions to a variety of areas. And Hungary issued a coin in his honor, and here are the pictures of those coins. And what you might notice here is a theorem of Chebyshev's, that there is a prime between every number n and twice the number, and that appears on the front of the coin, I think, and the back is the picture of Paul Erdős. Anyway, let's read what the probabilistic method is. The probabilistic method is a non-constructive method, primarily used in combinatorics and pioneered by Paul Erdős for proving the existence of a prescribed kind of mathematical object. And although the proof uses probability, the final conclusion is determined for certain without any possible error. Okay? So this is a somewhat of a paradoxical thing, that it is a probabilistic method, probabilities are involved, but in the end, you prove a statement, and there is no doubt about the statement. Okay? And of course, many of you have seen many sophisticated examples of this, so it's probably all superfluous for you. But those who have not seen this, yeah, I hope you get something out of this talk. So I'm going to, the first example is about polygons. So here are two polygons, yeah, this one and this one. But what I want to tell you about relates to convex polygons. So convex polygon is something like this, yeah? It has no cavities like this. Formally, if you have 2 points on the polygon, the line segment connecting them is entirely contained in the polygon. For example, this one is not a convex polygon because, for example, I could pick a point here and a point here and try to connect them, and then the line would leave the polygon. So it is not a convex polygon. Okay. So, all right. Sorry, am I doing something? Okay. So the next thing I want to tell you, again, this is probably middle school mathematics. Yeah. So what's the perimeter of a polygon? The perimeter of the polygon is just the sum of the lengths of its sides. Yeah. So here are two convex polygons, and I have somehow made up some lengths. of course, they are not accurate. And so the perimeter of the first polygon A is the sum of 3, 6. Okay, doesn't matter. Yeah. So no, as long as I am not at fault, it's fine. Yeah. So 3 plus 6 plus 5 plus 4 plus 7, that's the perimeter of the first polygon. And the perimeter of the second polygon is 8 plus 1 plus 7 plus 3. Yeah? Yeah. Okay, good. So now we know what a convex polygon is, and we know what a perimeter of a polygon is. Yeah, nothing. Okay. Now, so here is a polygon B, which is the outer polygon, and it contains in it an inner polygon A. Yeah? So it's a polygon A contained in another polygon B. Yeah? In this case, yeah, and both happen to be convex. Then the claim is that the perimeter of the inner polygon is less than or equal to the perimeter of the outer polygon. Okay? So it might look like a completely obvious statement. Yeah? If the same statement was made about the areas, that the area of the inner polygon is less than the area of the outer polygon, okay, I'm ready to believe it without any problem. But why is the perimeter of the inner polygon less than the outer polygon? Because the inner polygon could be nasty. It could have many, many, many sides. Yeah, of course, convex. But still, the inner polygon always has perimeter less than or equal to the outer polygon. Yeah. So what I want to show you today is a probabilistic proof of this. Okay, so where does probability arise? Yeah. So here's the proof. Yeah. It's okay. So should I just use this mic? Would that be better? Yeah. Hello. Yeah. Good. Yeah. So here's the idea. So I have written down a few steps here. So let's read them together. So let's draw a line. Yeah. Okay, doesn't matter. Yeah. So let's draw a line at random. Yeah. So you have these two polygons. You have these two polygons, and you draw a line at random, and you project orthogonally the two polygons onto this line. Okay. So the outer polygon B creates a little shadow here, and that I'm calling y, or the length of that shadow I call y, and the length of the shadow of the inner polygon I call x. Is this okay? Yeah. So clearly, since the inner polygon is inside the outer polygon, x is less than or equal to y. Is this much? Yeah. Because the inner polygon is inside the outer polygon, nothing to do with convex or anything. This is always true. So if I take this line at random, and over various lines, these shadows will have various lengths. But there is an average length that will arise. Okay? So that average length I denote by this. So what is the expectation of x? The average shadow length that A casts on this line. Average taken over what? The lines are generated uniformly at random. So x is the shadow of the polygon A, and y is the shadow of the polygon B. Okay. Sorry, you have a guess as to what I'm doing? I turned it off. Should I do something more drastic with it? It's okay, don't worry. Yeah, okay, good. So if x is always less than y, yeah, x and y are random variables, x is always less than y, clearly the expectation of x, the average value of x, is less than the average value of y. Okay? Now it turns out the average value of x
actually is proportional to the perimeter. That is, no matter which polygon you take, the average value of its projection onto a line is actually some fixed constant which doesn't depend on the polygon, times the perimeter. Okay? Now, we will see why that must be true. I'll invite you to think about it yourself. So, this expectation of x is actually proportional to the perimeter. Expectation of y is proportional to the perimeter of B. And since we know that this is less than or equal to this, the perimeter of A ought to be less than or equal to the perimeter of B. Okay. So, yeah, maybe, yeah, so why is it that the perimeter is proportional to the expectation of the shadow? Yeah? So let's look at one of the polygons. And this has 5 sides, S1, S2, S3, S4, S5. And we have picked a line at random. Of course, somehow my random line turned out to be horizontal here. Yeah? And this was the shadow cast by the polygon. But this shadow was made up of little shadows. Sorry. What happened? Yeah, little shadows that were cast by the individual edges. For example, S1, yeah, its shadow was X1. S5 was this. Now, as I go around the polygon, you will see that every point is counted twice. For example, the bottom chain of the polygon is accounted for by X1 and X5. But the top chain is accounted for by X2, X3, and X4, yeah? Their shadows. Okay. So here's something I've written. So the shadow, this shadow X, is X1 plus X2, so on till Xn divided by 2. When I add up all the shadows, yeah, there is a shadow from the top chain and the shadow from the bottom chain, and both are being counted. So if I add the lengths of all the shadows, then I ought to divide by 2 in order to get the length of the shadow of the polygon. Yeah, good. So everybody is okay with this? Yeah. Now I just take the expectation of both sides, and what do I get? The expectation of the shadow, that is the average shadow that the polygon casts, is actually the sum of the average shadows cast by individual edges, except that I have to add them up and divide by 2 because everything is being counted twice. So if I could show that when you take an edge and you ask what is its average length of a shadow, it depends only on the length because everything is symmetric. Yeah? So whether the length is long or short, and whether it is placed horizontally or vertically, if I pick a line at random and take the shadow of that edge or the line segment on this line, the average value will only depend on the length, and that is what justifies this proportionality, which means it is proportional to the perimeter. Now it turns out that this proportionality constant is actually 1 over pi, and the average length of the shadow is actually 1 over pi times the perimeter. Okay? And that is this proof. So, yeah, so I've done a little calculation here to show you why it should be 1 over pi. You probably did it all in your head, so it doesn't matter. Let me not tell you about this. So is this a big deal? Yeah, is this a big deal? I mean, after all, it's completely obvious. Most of us would have thought it's obvious that the inner polygon should have a smaller perimeter than the outer polygon. And if I perhaps challenged you to prove it to me, you would probably divide up this picture into little parts and do some combination of triangle inequalities show me that something on the left cancels with something on the right, and in the end, this equation emerges, okay, or this inequality emerges. But I hope you still appreciate the sort of painless way in which, by just thinking of the problem probabilistically, we are able to justify it. And in particular, if I gave you a convex body inside another convex polytope inside another convex polytope, do you believe that the surface area of the inner polytope is less than or equal to the surface area of the outer? We all would believe it for the same reason. And this time, trying to cut up the polytope by planes might look a little suspicious. Most of us can't imagine things in 3 dimensions. And what about 4 dimensions and 5 dimensions? Yeah. But the statement is always true. And for the same reason, because when we're talking about polytopes, instead of drawing a random line, what would we do? Just throw a random plane and ask, what is the expected amount of shadow that the polytope casts on that plane? And since the inner polytope is always inside the outer polytope, its shadow, on average, must be less than or equal to the shadow of the outer polytope, and the shadows will be proportional to the surface areas. I don't want to say more. Maybe we can talk about it later. Okay, so this was the first example where a theorem, perhaps not too surprising, about geometry was extracted out of some sort of a random thinking. Yeah. The point is that a shadow is some sort of an estimate of the perimeter, and those of you who do data science must have been told something called unbiased estimator. It turns out that the shadow is an unbiased estimator up to some normalization of the perimeter. And by comparing unbiased estimators, we are able to extract information about the original quantity. Yeah. Okay. So. All right. So yeah, let me move on to the next example. So. New thing. So this is about sets of numbers. So a set of numbers is said to be sum-free. Yeah, it's sum-free. Sorry, I kept moving away from the mic, but nobody objected, so I don't know if anybody's listening. Yeah. So, okay, good. So sum-free. Yeah. So what does sum-free mean? A set is sum-free if you cannot find 2 numbers from the set which added together yield a number from the set. So in particular, the set should not have the number 0. Yeah, yeah. So we are interested in finding sum-free sets. Sets where if you take 2 numbers from the set and add them, we don't get another number from the set. Okay? So for example, if you take the set of all odd numbers, take all odd numbers and add 2 of the odd numbers, it's going to give an even number. So the set of all odd numbers is a sum-free set. The set of all even numbers is not a sum-free set. Yeah. So here are squares of numbers. Now, yeah, squares of numbers. Okay, so maybe I should. Yeah, squares of numbers, are they sum-free? Well, you know that, yeah, what's it? 3 squared plus 4 squared is 5 squared. So it's not a sum-free set. But what about the cubes of numbers? Okay, so maybe I should mark. Yeah. So this one was sum-free. Yeah, I should use the margin. Yeah. Yeah. This is not sum-free. This is not sum-free. What about this? Yeah, because of Fermat's last theorem. Yeah. Okay. Yeah. What about powers of 2?
Yeah. Sum free, yeah. And the last one, yeah, I suppose 5 plus 12 is 17, so this is not sum free. Okay. So you understand what I mean by a sum free set, a set of numbers so that you cannot add two of them to produce another number in the set. Okay. Now, there is a theorem of Erdős that give me any set of n numbers. Give me any set of n numbers, I'll be able to get 1/3 of them which are sum free. Inside any set of n numbers, there is a subset, significantly large subset, 1/3 of the elements, so that they are sum free. Okay. And how do you prove this? And it will turn out that we will prove this using a probabilistic argument. Okay. So the idea is this. Actually, yeah, so here is your usual circle, and I'm going to use angles. So 0 degree, 1 degree, 2 degrees, so on, till 360 degrees. But I have written this in a fancier mathematical unit. So yeah, good. So what do I do? You've been given these elements from the set. You pick an angle. Sorry, this should have been omega. Maybe I should. Yeah, so pick an omega angle at random from 0 to 2 pi. Yeah? Pick an angle at random, and each of the elements, you multiply it with that angle, and you plot it here. So is it clear? So first pick an angle at random, omega. Then go to your first element of the set, multiply omega by that. Now this might involve, if b1 happens to be a very big integer and omega is some reasonable degree, it goes around and around the circle, and then it finally settles down somewhere. That is the position for b1. Then do it for b2, do it for bn. Okay. Now, collect all those elements which land up in this region from 2 pi over 3 to 4 pi over 3. Okay. That is my set. Now, clearly, any two elements here, if you add two angles which are in this sector, they will produce an angle outside the sector. Okay? So if you picked a random angle and mapped each element of your set to a point on this circle, those elements which happen to fall in this sector, they will all be sum free. Is this clear? Yeah. So if you, because if A plus B was equal to C, then A times omega plus B times omega would be C times omega. Okay? And we are doing angles modulo 2 pi, but you can convince yourself that it will all work out. Good. So all that we need to know is how big, how many of the elements are going to land up here. Now, the point is, the trick was our initial angle omega was uniformly chosen from the circle. So if you multiply this omega by an integer, it will still be uniformly distributed on the circle, which means if you pick any one integer and multiply it with a random angle, it's equally likely to fall anywhere in the circle. So it's likely to fall in this region with probability 1 in 3. So we expect 1 in 3 elements from this set to fall after we do this little maneuver on them. But all those elements which fall here are going to be sum free. Okay? So let me say it slightly better. So for each element
bi, this random variable xi is 0 if it doesn't fall in the sector, and 1 if that element bi falls in the sector. Okay. So the number of elements in our set A, yeah, A omega, is actually x1 plus x2 plus xn. This xi is 0 if it doesn't fall in this sector, and 1 if it falls in this sector. So, I mean, this is something we did last time, and the expectation of x1, what's the probability that x1 takes the value 1? Is 1/3, because it's equally likely to fall anywhere. Each of them has probability 1/3 of falling here, so this expected value is 1/3 n. Now, if some object has, or some random variable has expectation k, then there must be some point in your sample space when it takes the value k or higher. I mean, in a class of students, if everybody is, under 20 years of age, their average cannot be more than 20. Yeah? So for the same reason, because the expectation is more than 1/3 n, there must be a magic omega. There exists an omega for which 1/3 of the elements fall here. Okay? Which means those 1/3 elements from the set B are actually sum free. Okay? We did not break apart the set, did not think whether there were even numbers or odd numbers in them, etc. Just did a random argument, a probabilistic argument, and that gave us the conclusion that in any set, 1/3 of the elements are actually sum free. That is, there is a subset that you can extract from the set with 1/3 of the elements which are sum free. Okay, so I hope you like it. Yeah, I tried to illustrate it here, but I don't think you need that illustration. So yeah, so let me summarize again. So a fact was established with certainty. The theorem that every set has a subset of 1/3 the size that is sum free is not a probabilistic statement. Either it is true or not true. But in establishing that fact, we used a probabilistic experiment. Okay? Now, you can turn this method into an algorithm for finding this large set, yeah, which is sum free. And it turns out that this question has received a lot of attention in recent years. Many important conjectures made actually by Erdős were settled only recently. So in 2014, Abard, Green, and Manners, they showed that the constant 1/3 that we have is the best possible. That is, they can construct sets which are so awkward that you will not be able to extract more than 1/3 of the elements and still keep them self-free. The moment you try to get anything more than 1/3, yeah? Let's say instead of 0.33, you try to get 0.4 times n of those elements, then you will introduce a triple A, B, and C so that A plus B is equal to C. Okay? So yeah, this happened in 2014. Oh, what did I do? This is 2025. Yeah. Okay. So just this year, it was shown that you can improve this 1/3 by a tiny amount. Okay? But before this, even trying to improve this 1/3 n by 2 was considered a big challenge. There was a theorem of Bamberi, which had a very long proof, where he showed that it is not 1/3 n, it is 1/3 n plus 2, or something like that. Okay? But a graduate student from England recently showed that actually you can get 1/3 n plus constant times log n, but this says that you cannot get 1/3 n plus some constant times n. You cannot get 1/3 n plus epsilon n. You can get slightly better, but not much better. Okay. All right, so this was my second example. And yeah.
let you catch your breath and reorient yourself. So this is a problem in computer science of an algebraic nature. So what's the question? We have a binary operation on a set, and the operation is star. Okay, just give it the name star. And the operation is presented to us as an n cross n table. So what does this mean? A times B. A times B is A. C times D is C. So the entire binary operation has been given to us as this data. So if there are n elements in the set, the total amount of data here has n squared pieces of information. And the question is, determine if this operation is associative. Now, what does associative mean? I mean, we've been kind of tortured with this definition from school days. So if you take an element from the set, another element from the set, and another element from the set, and multiply them, there are two ways of putting the brackets. Either you multiply AI with the operation performed on AJ and AK, or you first perform the operation on AI and AJ, and then combine it with AK. If the two things yield the same result, then we say that it's associative. Otherwise, it's not associative. And now the question is, somebody gives you this table and asks you, is this operation, is this operation associative? Now, in this case, for this table, it turns out that there are these two triples for which associativity doesn't hold. But in general, if you're given this table, which is n cross n, how many steps do you need in order to verify that it's associative or it's not associative? Now, the obvious thing to do would be try every possibility for AI, every possibility for AJ, and every possibility for AK. Multiply them in the two ways and check. And how many ways are there to pick AI, AJ, and AK? N choices for AI, n choices for AJ, n choices for AK, n cubed possibilities. Can we do this faster than n cubed? And what I'm going to show you today is a remarkable algorithm of Rajagopalan and Schulman, which shows that you can do this with just n squared trials. You almost have looked at the table once. N squared is the amount of data in this table. Just constant times n squared. So you basically scanned the table a few times, and you'll be able to tell whether it is associative or not. You will not have to try all n cubed possibilities. Okay? Of course, there's a small probability of error, and if you want to reduce that probability of error, you repeat the algorithm a few times, and you can drive down the probability of error to any small constant you desire. Okay? So let me tell you what Rajagopalan and Schulman do. They pick random weights, W1, W2, Wn, from this set of size 6, 0, 1 to 5, and they consider this linear combination. What did I do? So this is just a formal linear combination. You have taken each element of this set, taken each element of the set, and attached in front of it a weight, 5 times A, 6 times B, 9 times C. So, sorry, not 5, 6, 9. The only numbers I'm allowed are 0 to 5. So 1 times 5, 4 times something, and so on. And now, this large object, you multiply in two ways. Now, what does it mean to multiply an object like this or an object like this with itself? Just open the brackets. The numbers get multiplied with the numbers, and the elements of the set get multiplied by the elements of the set. To multiply two numbers, use the same rules that you know about numbers, and for multiplying elements of the set with themselves, consult the table. Okay? So
you multiply this object with this object, what will you get? You will again get elements with weights. And then you again multiply them with that. You will get lots of elements, and associated with each element, a weight. You will get such an object from the left-hand side, and you will get such an object from the right-hand side. And just compare if all the elements receive the same weights in the computation on the left and in the computation of the right. If indeed this was an associative operation, this would be true. What you get on the left would naturally be equal to what you get on the right. There will be no problem. But if it was not associative, will you be able to catch it? Okay, so I'll say something. Yeah. So first of all, how much effort does it take? Well, any single multiplication takes n squared, because there are n coefficients here, n coefficients here. You multiply all of them, it's n squared amount of time. And then again, one more multiplication. So this requires 2n squared. This requires 2n squared. The total amount of effort is about 4n squared. I have written just n squared. So it's 4n squared effort. Okay. Now, so if you look at the left-hand side, yeah, what you get is these elements from the set, and attached to it are weights. And how are these weights obtained? You multiply an element from here, a weight from here, and a weight from here. And you add up all those combinations which give rise to AI, and you add them up. Okay. So each of the weights or the prefixes or the coefficients of the AI are actually polynomials in W1, W2, Wn, where this is W1, this is W2. Yeah, sorry, whatever. The n weights that we chose, W1 to Wn, each of them in the range 0 to 5. Okay. And similarly, the right-hand side also yields a polynomial in W1 to Wn. Polynomial of degree 3, yeah, in n variables. Now, if star was actually associative, then each of these polynomials would be equal to the corresponding polynomial that you obtained from the right-hand side. So any substitution, not necessarily from the range 0 to 5. If two polynomials are the same, you substitute the same values in them, they will still be the same. Okay? Yeah. These are polynomials on numbers. Huh? We are substituting numbers for the variables. What happens? So half the job is done. If it is actually associative, our test will say it is associative. But if it is not associative, what is not associative? If this table is not associative, what is the chance that we will catch it? Well, the point is, if there is even the slightest blemish, that is even one out of those n cubed possibilities, yeah, the left-hand side and the right-hand side did not match up. That is, there was a violation of associativity even in one place, then at least one of these polynomials will be different from the corresponding polynomial. For example, suppose it was the case that AI, AJ, AK were such that if you multiplied it this way, it yielded a different result than when you multiplied it this way. Then let AR be what is obtained here. Then clearly this quantity is not AR, because yeah, the left-hand side is not equal to the right-hand side. Now, if you look at the coefficient of AR in this, the coefficient of AR here, when I is equal to, when this I is R, the corresponding thing will be PR. And in that PR, W1, W2, sorry, Wi, Wj, Wk will be a monomial. But AI, Aj, Ak on this side does not yield AR. So Wi, Wj, Wk will not appear in the corresponding polynomial here. Yeah. So now, if you have two polynomials of degree 3 and you substitute random values for them, what's the probability that by coincidence, by chance, they become the same? the difference of these two polynomials, so at least for one variable, if you have two polynomials of degree 3, which are different, their difference is also a polynomial of degree at most 3. Yes? And it's a non-zero polynomial. A non-zero polynomial of degree 3 can have at most 3 roots. So if you pick an element from the range 0 to 5 and substitute it, the chances that you would have hit the root is only 3 out of 6. That means at most half. Okay? Nothing I said was particular about polynomials in one variable. If you have a polynomial of degree 3 in n variables, and you pick substitute for them values in the range 0 to 5, the chances that the two polynomials will become the same, will evaluate to the same value, is at most half. So that's it. If it is not associative, this test would catch it with probability half. And if it is associative, there is no chance of error at all. Okay? And if you want this half to be 1/4, do the experiment once more. Yeah? That you were unlucky on both your trials would be half times half, at most 1/4. Okay? So what looked like a definition which demanded n cubes amount of work, if you're allowed a small amount of error, can actually be verified using only n squared amounts of work. Okay? And this is why randomness plays an important role in computation. Now, yeah, that is, I could have given, or I thought about giving a talk on randomness and computation, but that was not the road I took. But if I had taken that road, I would have told you about randomized algorithms. Perhaps I would have might have been tempted to tell you about pseudo-randomness, de-randomization, average case analysis, construction of combinatorial objects using sampling, cryptography, security, privacy, error-correcting codes, information theory, maybe quantum algorithms and information. The point is, probability is very important to computation. Okay? But what we did were 3 small examples about the probabilistic method. Now, randomness has been central to computation for over 4 or 5 decades. And I just want to leave you with a quotation from a book in 1989. Silvio Micali, a very famous cryptographer, he edited this volume of articles on randomness and computation in 1989. So let me read what he said then. So why have we realized that randomness can be used in computation? That is, why now? Here is my explanation. I believe the main reason to be that we have become increasingly comfortable in living with uncertainty. The uncertainty, I mean, of human survival. Only after having achieved a good chance of nuclear and ecological disaster could, for instance, the notion of a proof that has a controllable chance of being false become so readily acceptable. It is true, to be fair, that nowadays the individual experiences a longer and safer life, but humanity as a whole stands at greater risk. Science is primarily a social enterprise. It is this common risk that has paved the way to accepting previously too daring scientific and thus eminently social concepts, exciting times indeed, scientifically and otherwise. Now, this is how he perceived risk in 1989. I suppose the world is safer now. So in any case, I let you think about it. Make use of randomness in this uncertain world. Yeah. I wish you the very best in your journeys ahead. So thank you very much for listening to me. Congratulations again. So, yeah, if there was, I'm sure I wasn't very clear, but
if you would like something to be explained, or if you think others can benefit from my explanation, please ask. Yeah. So again, yeah. So we had 3 examples, just to remind you. The first was about the polygon. Yeah. So I'll wait for your question. So the first was about polygons. The second was about sum set, and the third was an algorithm for testing associativity. Yeah. Questions, sir? Yeah. So I don't know if the mic needs to be passed. But no, please, sir. Yeah. No, so I think you, at least for the first 2 examples, it was symmetry, or at least we've enforced symmetry on the problem. Yeah. So we thought if the numbers were random, what would they look like? Yeah. And if we picked random numbers at random on a circle, 1/3 of them will fall in that sector, in the forbidden sector, or the convenient sector. Now our set is not random. It is somebody who's given us the set adversarially. But we notice that we can spin the set by the angle theta. And each element somehow has its own life when it's multiplied by theta. And each element somehow symmetrically moves around the circle and lands up in the desired region with probability 1/3. So we enforce symmetry. In the first question about polygons, yeah, there was a line. The polygon had these little sides which were rigid, attached to each other, but we decided just to view the polygon from a random angle, yeah, and which turned things into made things symmetrical and helped us with the calculation. Now the third problem, I'm not completely sure we really use symmetry. We didn't permute the elements or things like that, but there is an important interaction between algebra and randomness, most of the time mediated through this simple principle that a polynomial of small degree cannot have too many roots. Okay? So yeah, so I agree partly with you that at least 2 of the examples owe their existence to symmetry, or in our recognizing symmetry in the problem. Yeah. Questions? Yeah, please. That's right. Okay, so there is a related thing. I mean, that is a textbook example, and I wanted to avoid that. So suppose you've been given an n cross n matrix A, n cross n matrix B, and an n cross n matrix C, and you are asked to verify if A times B is equal to C. Yeah? Now, what do you do? Well, you could compute the left-hand side, and how much effort does it take? Well, to compute each entry of the matrix A times B, you would need to multiply a row with a column, if old-fashioned way, and that would require n-cubed amounts of effort. Yeah? But if you notice that the left-hand side and the right-hand side are actually not inert arrays of numbers, but they're actually linear transformations. A matrix is a linear transformation. And 2 linear transformations which are different disagree almost everywhere. So what do? Pick a vector at random and multiply it with the matrix on the right and the matrix on the left. But the matrix on the left is A times B times the vector. So first multiply B times V, requires only n squared multiplications. Then multiply the result with A times V, again only n squared multiplication. And you have been able to verify whether A times B is equal to C with only n squared multiplication. So I agree, we turned what looked like a problem on sets into multiplication. Actually, although I have written it as polynomials, these are just, you can call it an algebra, where you have these vectors, where W1, W2, Wn are the coefficients, and you are multiplying them. So any equational system where the violation would lead to 2 polynomials which are different can be verified by substituting values. Yeah. Thank you. Yeah. Question? Yeah.
What's so special about that number 5? Like,
Number 5. What was so special about number 5?
Yeah.
There was nothing. I just wanted a nice probability of half. So it was 3 divided by 6. 0 to 5 is 6. That is special about 5. Yeah.
I was wondering maybe it was like a size of 6, a set of size 6.
So it was any set of size 6. Now, while doing these computations, of course, when you multiply two numbers, numbers tend to become big. So often such computations are not done over integers, but over, say, you just take mod something. And the most natural number, most convenient number to use here would have been 7, because numbers 0 to 6 form a field. And you do the operation on the left-hand side and right-hand side modulo 7.
Okay. And does 0 need to be there?
No,
1 to 7,
any 6 numbers would have been there. 0 did not have any special role here. Okay. Yeah, except that perhaps while doing computation, multiplication by 0 is especially pleasant. Yeah. All right. Good question. Oh. Yeah. Thank you very much for being patient.
So I hereby dissolve the conversation. I welcome you to join us outside for some tea and snacks.
Graduating students, please hold on. We'll have some photography. Group photos. Please come. Please wait. Okay. No, those were like very cluttered. Gold medalists also, please wait. All the students, please wait. Please hold on. We'll have group photos. Proper group photos. Sumit Rajput. Is Sumit Rajput here? Ryan? Ryan Hota? Okay, BSc students, BSc Maths and CS, please come over. Maths and CS first. Huh? Suchit, 1 second. By the way, this gold medal is real gold.
Oh, really?
Okay, it's not plated, yeah.
Oh.
Okay, so I want an acknowledgement from you that you have received it.
Sure. There will be a separate photo for gold medalists?
No.
Okay, just I can go back, no?
Yeah.
Okay.